The most common kind of planet in the galaxy is one you have never stood on and never will. Astronomers call it a super-Earth, a world somewhere between 1¼ and 2 times Earth's width, or by NASA's summary, up to about 10 times Earth's mass. Big enough to hold a thick atmosphere. Small enough to still have ground under it. Nobody voted on those boundaries, but the census is clear, and NASA's exoplanet pages put it flatly. Super-Earths are common among the planets we have found, and we have nothing like them in our own solar system. Kepler, which confirmed more than 2,600 worlds before it ran out of fuel, put it harder. The most common size of planet Kepler found doesn't exist here. Our system skipped the model the galaxy builds most often. So here's what one would do to you. Start with the strangest feature in the data. In 2017, Benjamin Fulton and the California-Kepler Survey team measured 2,025 planets precisely enough to sort them by size, and they found a hole. Worlds pile up below about 1½ Earth radius. They pile up again between 2 and 3. In between, the count drops by at least a factor of 2. Astronomers call it the radius valley or the Fulton gap. It isn't a gentle dip. It's a groove cut into the galaxy's population, right where a super-Earth stops being a rock. Two explanations compete, and both might be right. Owen and Wu argued that the star does it. Ultraviolet and X-ray glare from a young sun boils the hydrogen envelope off a close-in planet, and the bare core is what survives. Ginzburg, Schlichting and Sari proposed something quieter, where the planet's own leftover heat of formation pushes the air away from underneath. Either way, a thin hydrogen envelope is unstable. A planet keeps a big one or loses the lot, and the middle sizes drain out. Leslie Rogers pinned down what that means for you in 2015 in a paper whose title is The Whole Finding. Most 1.6 Earth radius planets are not rocky. Above that line, the ground tends to stop existing. One world makes the point brutally. TOI 849b circles its star every 18 hours, roughly 735 light-years away, and when David Armstrong's team published it in Nature in 2020, the numbers looked wrong. About 3½ times Earth's radius. 39 times Earth's mass. That's roughly Earth's density packed into a body nearly the size of Neptune. Astronomers settled on the reading that TOI 849b is a naked core, the rock and metal heart of a giant that lost its atmosphere or never assembled one. It's what the radius valley leaves behind. Now pick a gentler world and go stand on it. LHS 1140b orbits a small red star about 49 light-years away, and in 2024, Charles Cadier's team measured it at 1.73 times Earth's radius and 5.6 times Earth's mass. Run those through the surface gravity formula, and you get close to 1.9 times Earth's pull. Your body would file a complaint within seconds. Blood would settle low in your legs. Your heart would work harder for every minute you stayed on your feet, and a stumble would become a fall you couldn't correct, because everything drops faster there. Standing still is exercise. The air would be different too, and mostly in your favor. A heavier planet grips its gases harder, so a super-Earth tends to keep the atmosphere that Earth slowly bleeds into space. More nitrogen, deeper cloud, better shielding against cosmic rays. When Webb looked at LHS 1140b, the data killed the puffy hydrogen envelope of a mini-Neptune outright, ruled out past 10 sigma. What survives is either bare rock or an atmosphere of heavy molecules, and the best fit was a nitrogen-dominated one, though only at 2.3 sigma, which is a hint and not a result. Under that, a world carrying 9 to 19% of its mass as water. If the water world reading is right, the team's climate model puts liquid water at the point directly beneath the star across a wide range of atmospheres, a warm eye of ocean set in a frozen shell. A real place, with weather 49 light years from this sentence. Here's the part that should bother you. Gravity strong enough to hold an atmosphere is also strong enough to hold everything else, and rockets are exponentially bad at arguing with gravity. In 2018, Michael Hipke worked the numbers for Kepler-20b, the largest rocky planet known at the time, about 1.87 times Earth's radius and 9.7 times its mass. Take a 10 Earth mass version of that world and escape velocity comes out near 27 kilometers per second against our 11. Push that through the rocket equation and a single-stage launch has to burn 104 times the fuel it burns on Earth. To lift a payload the size of the James Webb Telescope, 6.2 tons, you would need 55,000 tons of propellant, about the displacement of a battleship. An Apollo-class mission would call for a rocket near 400,000 tons. Hipke's verdict was that chemical rockets still work up to around 10 Earth masses. Barely. Past that the fuel bill runs away from you. He looked at the space elevator as the way out and doubted it. Carbon nanotubes are only just strong enough for Earth, and nobody knows whether a stronger material is physically possible at all. That leaves nuclear propulsion, which a civilization would have to invent before it had ever seen its own planet from outside. Every launch is a national effort. No cheap orbit. No swarm of weather satellites, and certainly no casual trip to a moon. A thinking species could evolve on the galaxy's most ordinary world and find the door bolted from the inside. So is a super-Earth a better address than this one or a worse one? Serious people argue both. In 2020, Dirk Schulze-Markuch, René Heller and Edward Ginnen published a paper in Astrobiology making the case that our planet isn't the ceiling. Their sweet spot is a planet about half again as massive as Earth and roughly 10% wider, orbiting a cool orange K-dwarf. Those stars burn steadily for tens of billions of years. Our own sun gives Earth about 1 more billion years before its rising output pushes us out of the habitable zone. More land, more shallow sea, more time. They pulled 24 candidates out of the catalogue. Then they added, carefully, that not one has been shown to hold anything alive. The geology is a real fight. Diana Valencia's group argued in 2007 that plate tectonics on a super-Earth is inevitable, since thinner plates under stronger driving stress should subduct more easily. That machinery recycles carbon and holds a climate steady across geological time. The same year, Craig O'Neill and Adrian Lenardic ran their own models and got the opposite answer. Scale a planet up and it locks into a stagnant lid, one unbroken shell with nowhere for the crust to go. Both papers are still in circulation. Jun Cornaga later suggested that size may matter far less than whether the world has surface water, which is a courteous way of saying nobody knows. Caution belongs in the answer, and the last 2 years showed why. K2-18b lies 124 light-years out, about 2.5 times Earth's radius. In 2023, and again in April 2025, Niku Madhusudhan's team reported a possible trace of dimethyl sulfide in its atmosphere, a gas that on Earth comes almost entirely from marine life. The headlines wrote themselves. Then other groups went back to the data. Raphael Luke's team re-reduced the Webb observations with 3 independent pipelines, then modeled the whole spectrum at once instead of one instrument at a time. Their verdict: no statistical significance for the molecule at all. A separate team under Owen Wu at NASA's Jet Propulsion Laboratory, working from a wider set of Webb observations, found nothing above 3 sigma, nowhere near the 5 that a claim like this demands, and noted that plain chemistry in a hydrogen atmosphere can make the same gas with no biology involved. The signal might survive. It hasn't earned the word yet. Step back and the picture inverts. We were raised to treat Earth as the standard and everything else as a variation. The catalogue says otherwise. Out of more than 6,000 confirmed planets, the size the galaxy keeps returning to is a size we don't have, and the modest rock underfoot is the strange one. Somewhere out there, on a world half again as wide as this, something heavy-boned may be looking up at stars it can measure and cannot reach, running Hip's arithmetic and getting Hip's answer. We drew the small planet. 11 kilometers a second, and the sky opens. Nobody arranged that for us. It's a piece of luck written into the mass of the ground beneath our feet, and we have already spent some of it walking on another world.